The Red Bull ring is short, just 10 corners, but that doesn't mean that setup is made simple. You have altitude reducing downforce, you've got aggressive curbs testing your suspension geometry, and you have 3 major braking zones that punish weak energy recovery systems or brake ducts. The Red Bull Ring Alpine Circuit has a track length of about 4.318 kilometers, rising to a maximum altitude of 660 meters above sea level. The elevation change is about 65 meters per lap, and drivers spend about 73.75% of that lap at full throttle. Lower air density means significant aerodynamic challenges. Formula One aero packages are designed to maximize downforce, which is a vertical force that pushes a car downwards towards the ground, increasing grip and allowing for faster cornering for the cost of increased drag. Downforce is the opposite of lift. Aeroplane wings generate lift, which is an upwards vertical force. By inverting the cross-section of an aeroplane wing, we create a Formula One downforce wing. The amount of downforce generated can then be worked out by using the lift equation, which is lift equals a half CL rho V squared A. Taking a closer look, CL is the coefficient of lift. Once the wing is designed and made in the factory, this coefficient will be mostly constant throughout the race weekend. Rho is the air density. This is the important factor at the Red Bull ring. V is the car's speed, which we square in this lift equation, before multiplying by the reference area of the wing. As we increase altitude, air density goes down, and this is because there's less air molecules above pressing down, so the air column weighs less per unit volume. This results in lower air mass and fewer oxygen molecules for combustion and aerodynamic force generation. At 660 meters above sea level, rho reduces from its value of 1.225 kilograms per meters cubed to just 1.14, which, when you plug it back into the lift equation, corresponds to about a 7% decrease in downforce. One way you can recover the lost downforce is to use a larger wing. A higher reference area means a larger value for A and hence more downforce. But the trade-off by doing that is that drag and downforce are directly linked by their component. The drag equation is drag equals a half CD rho Vmax squared A, where this time CD is the coefficient of drag. For a given wing shape, the reference area A appears in both the downforce and drag equations. Since the coefficient of lift is typically much higher than the coefficient of drag, increasing A gives you more downforce but also more drag, though proportionally less. That added drag increases aerodynamic resistance at high speeds, which limits the car's top speed, as the engine has to work harder to overcome it. It's why Austria forces a compromise. You can't just bolt on Monaco-level downforce packages, because you will just get overtaken on the long straights. Engineers often aim for a medium to low downforce aero package, often specifically for this race. Austria's curbs are harsh, especially between turns 7 and 9. You need suspension stiff enough to stop the floor from bottoming out as you go across, but not so loose that the tires lose their contact patch with the curbs and hence lose their grip. Spring rate K defines the force needed for 1 mm of compression. If the suspension is too soft, ride height drops and the floor will stall, reducing downforce. If it's too stiff, however, the tire contact patch reduces over curbs, leading to a loss of grip. Dampers add a force that is proportional to velocity, Fd equals Cv, where C is a damping coefficient. Damping is tuned to control oscillations without over-restricting the suspension's freedom to move. Ride height is critical for ground effect floors, and this is because the closer you can be to the ground, the greater the Venturi effect you will have, but you do run the risk of bottoming out. The Venturi effect occurs when air flows through a narrow section of the car's floor or diffuser, causing the air velocity to increase and pressure to drop. This lower pressure under the car essentially sucks the car towards the track, generating downforce without adding drag. Engineers can simulate the ride response over curbs using multi-body simulation tools such as Adams, and then validate those simulations using 7-point rig testing and fine-tune their damper curves. Into turn 1, cars experience a massive energy dump. Peak braking is at around 5 G, and carbon-to-carbon brake disc temperatures rise to about 1000 degrees Celsius. Per braking event, kinetic energy is shed, which is governed by the KE equation. EK equals a half mv squared. For a car braking from about 320 kilometers per hour to 100, which in meters per second is 89 to 28, for a 798 kilogram F1 car, using the KE equation from earlier, this gives us 2.6 times 10 to the 6 joules per braking event. That's over 2.5 times the energy in a stick of dynamite dumped into the brakes in just 2 seconds. Turn 2 is a flat-out left kink, often known as the fastest corner on the track and taken at about 290 km per hour. Turn 2 flows into the low-speed hairpin of Turn 3, which provides a massive traction demand. Teams may use slightly softer rear anti-roll bars here, or tweak diff preload to improve the exit grip. The focus here is on traction, rear longevity, and throttle on balance, as a good exit here is essential to get down the 3 to 4 DRS straight. Turn 4 at the Red Bull Ring is deceptively simple. A downhill braking zone into a medium speed right-hander. But from an engineering point of view, it's nothing but simple. There's a lot of physics taking place here. First up is load transfer. As the car decelerates, inertia shifts weight forward, and because turn 4 is downhill, gravity adds to that effect. The formula is change in force equals car mass times deceleration times the height of the center of gravity, all divided by the wheelbase. This load transfer puts more weight on the car's front axle, which is great for front grip, but can easily overload the tires and cause the fronts to lock up into the corner. Next is the aerodynamic consideration. The car's downforce isn't applied evenly across the whole car, it's distributed. The balance point for the aero forces is called the center of pressure. It's the point where all the aerodynamic forces effectively act, and where they produce no net torque on the car. Meanwhile, the center of mass defines where the mechanical load transfers around. When both are aligned, the car is predictable, but when they're mismatched, things start to get tricky. Under braking, especially with rake, which is where the rear of the car sits higher than the front, the aerodynamic center of pressure often moves forward. That adds even more load to the front axle. The challenge is to maintain both mechanical and aerodynamic load transfers simultaneously. Engineers can deal with this in a few different ways. First is brake migration, dynamically shifting brake bias rearward during braking to reduce front locking, which can be done by the driver themselves. Next is rake tuning, where you adjust the front to rear ride height to position the center of pressure more carefully. You can also adjust the suspension stiffness, softening or stiffening springs to manage how quickly the load transfers and where it settles. And finally, you can also look at the weight distribution, which is the fixed placement of heavy components such as the engine, fuel tank and driver, which define the base center of gravity. It's important to note that while setup changes can redistribute how load is transferred between the front and rear axle, it can't reduce the total amount of load transfer. That part is just defined by physics, and engineers have to just manage where it goes. And that is called mechanical balance. In turns 5 through 6, these medium sweepers test lateral stability. Aero balance is king here. Teams may tweak their front wing flap angle and floor edge vortices to tune mid-corner balance. Turns 7 through 9 is all about curb survival. It's where suspension kinematics really matter the most. Teams try to manage grip, whilst adjusting the travel range of the suspension to accommodate for the curbs. Turn 10 is the final corner and it's a high-speed one. Cars must rotate without oversteer. Aero balance and rear stability are the targets here. Engineers may run slightly more rear wing than normal here to take advantage of the extra rear downforce and keep the rear planted. At this altitude, there's less oxygen in the air. That means that combustion is less efficient. But thanks to turbocharging, F1 engines can compensate. The turbo simply spins faster to compress more air. But because it's spinning faster, it generates more heat, which brings back the cooling issue. To deal with it, engineers might open up more bodywork on the car than normal, enlarge cooling inlets, or add gurney flaps in to aid with extraction. But each of these additions add drag, so it is a balance. Too hot, and you cook the engine. Too much drag, and you'll get overtaken on the straight. So yeah, the Red Bull Ring isn't just about sending it up the hill. It's a full spectrum engineering challenge, from fluid dynamics to thermal management to mechanical tuning. If you want to win here, you don't just need a fast car, you need an adaptable one. If you want more engineering focused F1 breakdowns, subscribe and stay tuned. Until next time.